Hi everybody, this is Mr. Folly, and this podcast is one of the different ones that we go through it. I'm going to teach you how to use Lewis dot structures, which teaches you how to arrange molecules for the different atoms in a molecule to make sure it goes through the right shape. I'm going to give you what these letters mean and how it affects shape, and we're going to go through every possible shape that you will need to know in one podcast, and there's quite a few of them. So basically what I want you to do once I start drawing the shapes is watch me draw the shape and then pause it and try and draw it then. And all the images I got, I just Google image the name of the shape. A dude named Lewis thought of how to arrange atoms as molecules, and this is based on valence electrons. So if you have a periodic table handy, if not, get one out. Hydrogen is in the first column, so it has one valence electron. Calcium is in the second column, so it would have, when it bonds, it has two singles, but then that's the way I'll show it because we're bonding for all of these. Aluminum has three valence electrons, 1, 2, 3 singles. And this is the way it looks when it bonds. Carbon has 4 singles because it's in the fourth column of the periodic table. We've done tons of stuff with valence electrons all over the place. Nitrogen has 5, 2, 3, 4, and what you get is you get a pair and 3 singles. There are only 4 regions that we're going to deal with for electrons. We're talking about atoms by themselves. Oxygen has 6, so it would have 2 pairs and 2 singles. And what's kind of nice about this is single electrons are called radicals. So if you hear about free radicals in food and stuff like that, boy, my A's didn't turn out very well. Those are things that react very quickly. And free radicals are bad because they tend to react with things you don't want them to, like DNA and things like that. Chlorine has 7. 1, 2, 3, 4, 5, 6, 7. And again, looking at single electrons implies usually how many bonds they'll have. So hydrogen will form 1 bond because it has 1 single. Calcium 2, it has 2 singles. Aluminum 3, it has 3 singles. Carbon 4, it has 4 singles. Nitrogen has 3 singles, so it forms 3 bonds. Oxygen has 2 singles, 2 bonds, H2O. Chlorine has 1 single, 1 bond. And krypton is all pairs, so it has no singles, so it forms 0 bonds. So hopefully that'll help figure out why noble gases don't react much. Bonds formed by connecting the dots. And there's some steps that I wanted to go over first, but I guess I'll do it this way. Carbon, 1, 2, 3, 4 singles. And then since I have 4 hydrogens, I kind of aim them at my single electrons. Connect the dots, la, la, la. Connect the dots, la, la. Now I said quickly that you can figure out how many electrons something brings in by looking at its number of valence electrons. And I should have actually drawn that for the people. And there's probably a ton of us that have forgotten. 1 valence, 2 valence, skip the D block. And then 3, 4, 5, 6, 7, 8. So 3 through 8. And you can figure out from there, from your great counting skills. Nitrogen, or I'm sorry, ammonia is NH3. N, 1, 2, 3, 4, 5. H, every H has 1. I'm going to aim them at the single electrons. And then connect the dots, la, la, la. Nitrogen, it's N2, and I'm going to do this just a little bit differently. Nitrogen, I know, has 5 electrons, and I know it's diatomic, so I'm going to aim my single electrons at it. So notice I put my pairs far away, because they won't be bonding. And then there's a single bond, and then what can happen after that is these single electrons have to be taken care of. You can't have single electrons. It's one of the big rules of these things. So you can think of these 2 as moving down, these 2 as moving up. And then what you get, then you can connect those dots. So essentially what you get is N with a triple bond to each other. Okay. Now, it's very important that these atoms, remember, 8 is great and 8 is stable. So we want, because 8 is full, we want to make sure that every atom has 8 that's supposed to. The ones that don't have 8 are hydrogen. It's on the top row. It only needs 2. But besides that, pretty much everything should have 8. The exceptions, again, the exceptions are on a later page, but here we go. So the way I'm going to count this, I suppose I'm going to dream that my highlighter will work today, and it won't. Oh, maybe my highlighter needs to be in a bigger. Better. Okay. So that was my problem. Okay, so carbon 2, 4, 6, 8 electrons, which makes it happy. And hydrogen, which I'll highlight in red, has 2. Notice how it counts twice. 4, 6, 8. So those electrons can count for both carbon and hydrogen. So looking at hydrogen again for ammonia and H3, 2, 4, 6, well, not 2, 4, 6. That hydrogen has 2. The bottom hydrogen has 2. The right side hydrogen has 2. Looking at ammonia, I'll go green for that. It gets 2 for its lone pair, plus 2 for the bond. So pair, 4, 6, 8. Okay. And N2 has 8 as well. I'm glad I figured out why my highlighter didn't work. CO2, carbon, 1, 2, 3, 4. Oxygen has 6. 1, 2, 3, 4, 5, 6. Notice how I aimed, again, my single electrons at each other. So connect the dots, la, la, la. Connect the dots, la, la. Now, again, I have single electrons, so what I'm going to do, instead of drawing a little arrow showing they move them, I can connect those dots, la, la, la. Connect the dots, la, la. Now, that looks ugly, and I would not give you credit for something that looks like that. You need to redraw it to make it prettier, meaning just make your bonds look special and important. And all that matters is that oxygen has 2 pairs and a double bond. There's the double. And carbon would have 2 double bonds, double bond on the left, double bond on the right, and the actions would be the same. And that's it. By the way, quick review. CO2 would have 2 sigma bonds, 2 pi bonds. The first bond is the sigma, second bond is the pi. Looking at nitrogen, N2 with that triple bond, it would have 1 sigma and 2 pi. So how do we do this? Making Lewis in 3D shapes for molecular compounds only. So molecular means 2 nonmetals. The least frequently, or carbon. Carbon always goes in the middle. Put on the valence electrons, which is what we did before. Connect the dots, la, la, la. Make double and triple bonds if necessary. By the way, if you're writing these down, we're going to use them so much you probably don't even need to. There is one rule you need to write down. Only the central atom can break the octet rule. The third row or below can be bigger. So being bigger means breaking the octet rule means it can have 10 or 12 electrons. The aluminum group can be smaller, which would be aluminum and boron only. And they will have 6, not 8. And remember, you are the master of the electrons. You can pick up an electron and put it anywhere your little heart desires. This is the question people miss on the tests and on the quiz. What does VSEPR stand for? You need to say valence, shell, electron, pair, repulsion. Yes, I called it VSEPR, which sounds like it's VSEPR. But it's spelled VSEPR, whatever. But it's always pronounced VSEPR. Electrons are always in pairs, hence the pair, hence the electrons. Electrons push each other away, hence the repulsion. And it tells us the shape. So valence means the outer electrons. So the outer shell electron pairs push each other away. And depending on how hard they push, that'll determine the shape. Linear. MgCl is an ionic compound because it's a metal and a nonmetal, and ionics don't really do this, but this is the simplest form of a linear thing. Magnesium would bring in 2 valence electrons. Chlorine would bring in 7. Magnesium goes in the middle, it's the least frequently occurring. By the way, you can abbreviate pairs by drawing lines like this. So to show you what I mean by that, I drew the dots for the pairs on the left-hand chlorine, and I used the lines on the right-hand pair. Now I've got this set up. I've aimed my single electrons at each other. Connect the dots, La, la, la. The reason why ionics don't do this is this is an ionic bond, and notice how magnesium has 4, which you'd think would be bad, but that's because magnesium doesn't really do this. But every once in a while we throw something like that at you. So when I told you aluminum and boron are happy with 6, so that means that, remember, magnesium would be happy with 4. Anything in the alkaline earth metals would be happy with 4. The better way to do linear is HCN. Again, when in doubt, carbon goes in the middle, least frequently occurring one, or carbon. So carbon goes in the middle, H goes on the end, 1 electron. Nitrogen goes in the other end. Its spot on the periodic table, again, tells me how many valence electrons. 5th column does that. 5. Connect the dots. La, la, la. Ooh, oh, look. Double bond. No, it's triple. And then I would rewrite this H, C, N. Now, why is this shape linear? There are 2 regions of negativity. The first region is on the left, and the second region is on the right. Now, I know it's a triple bond, but it's still going to have the same repulsion. It's a region of negativity. They're going to be as far apart from each other as possible, and that would be 180 degrees. Same thing would be true up here, right? The next type is trigonal, planar, and bent. Again, you should be looking at that sheet I told you to have handy for the pictures. Boron and aluminum typically do this trigonal planar because you're breaking the octet rule on the small side. It can also be done with double bonds, but you get the idea. Boron goes in the middle, least frequently occurring. So F has 7. It's a halogen. Didn't give myself a lot of room. Should have. Connect the dots. La, la, la. Now on this appears to be a 90-degree angle, but it is not a 90-degree angle because this angle over here would be 180. These things are going to push each other away, and it's going to end up looking like this. The bond angle here is 120. Bond angle here is 120. Bond angle here is 120, and that's spread out much better. Okay, so that's it. Bent. HNO. The way it's written helps too. Since it's written with N in the middle, we'll put N in the middle. 1, 2, 3, 4, 5. Should make dots look a little better. Put an H over here with a single electron. O over here, 2 pairs, and single. Again, the valence electrons are determined by their place in the periodic table. Oh, look, I have single electrons aimed at each other. Even if I put the single electron up here, as master of the electron, I can change it and just change places with it as long as it's still the same number. So this is going to form a double bond, which should be, oops, whoa. Let's start all over again. H, N, double bonded, O with a pair. Now in this case, this would be bent because that lone pair pushes just like the bonds push. And lone pairs actually push a little bit harder. Not much, but a little bit. So before we would have expected the bond angles to be 120. Let me redraw this up here a little bit better. You'd expect a 120 to the pair, and a 120 to the pair. But because the bonds push harder, this angle would really be something like 118. As long as you say a little bit smaller than 120, you're fine. Tetrahedral, pyramidal, and bent. This is tetrahedral. This is pyramidal, and bent was just like the last one was bent. Okay. So CH4, to draw that one, C, and now the H's go around, and H have 1 electron. Now there I've got 4 regions of negativity, and looking at it, it's like, oh, good. That would be 90 degrees. But 90 degrees is not as good, although my number looks like a 70 degrees, not as good as that picture shows where every bond angle is 109.5. Well, if models where we look at that, we'll be able to see that that's better. The way you need to be able to recognize these as being drawn is like this. Okay, so I think you can tell that this leg right here is fading in the background. That's why this is a dashed line. and then this one's coming out at you, which is why this is a wedge, and this one's in the same plane as the paper, which is why that's a regular line. Okay, now NH3. All right, the next one is NH3, and NH3, again, looks like that, which would be pyramidal. And the Lewis dot structure, which is not 3D, would look like this. And you can tell that these electrons would push down, so there's 4 regions, just like on this one. So the difference is, instead of having this be a bond, it's a lone pair, so there's a lone pair up here. The way you draw this would be having this to make it similar to this. Same plane. This would be busting out. And this back one would be dashed to show that. And then I always show the lone pair, although that's not necessary. Water is bent. If I just kind of got rid of this part in its entirety, I would see a bent molecule like this. I always say water looks like Mickey Mouse, and this would be the head with the ears. This would be the upside down Mickey Mouse. But water would look, I suppose I should just make the oxygens. And if you made these circles as atoms, ta-da, it looks like Mickey Mouse. The bond angle for tetrahedral is 109.5, and H3 has a lone pair, so it's a little bit less. It's 107, and this is on your sheet. And water is about 105. Whoops, I'm going to put 150. You should have rough ideas of the bond angles. Trigonal bipyramidal seesaw shape. Okay, this is trigonal bipyramidal shape. Okay, that's kind of a weird shape. This one is seesaw. You can tell if I knocked it over, it could make like a little teeter-totter or seesaw or whatever it is. So I'm going to go ahead and first draw dot structures for these. So P has 5 valence electrons. F has 7, again with one single, connecting the dots. And then I've run into an issue here because I need a 5th one. And if I do this, I'm breaking one of the rules, which is trying to obey the octet rule. Because right now, phosphorus would have 2, 4, 6, 8, 10. Now, all of the fluorines would have 8, which would be fine. But phosphorus has 10, so you need to consider, is that okay for phosphorus? Phosphorus is on the 3rd row, and the 3rd row has 3d electrons to promote into, and we will talk about that in class a little bit more. But you need to be on the 3rd energy level or below to break the octet rule on the big side. So that would be PF5, and if you can see you've got 5 regions of negativity here, you would be able to separate them like this, and the biggest distance you would have, the bond angles on the axis would be 120, and the bond angles from the top and bottom to that would be 90. Okay. SF4 is quite similar to that. It would have one lone pair. So if you see how this is rotated, it's flipped 180 degrees, the lone pair would be located right there. So sulfur would start with S. Well, actually, you know what? I'm going to take this shape and just do BrF3 with it because I've got this space here. So bromine has 7 electrons. And 3 fluorines. Now, I only have one single electron to aim at it, so I'll do that. Again, fluorine has 7. That's a single bond. So it's going to have one bonding site. Now, what happens here for T-shape, this should be BrF3 negative, by the way. Not negative, positive. What happens here is, oh, no, it does not, it's my bad. That's what I get for doubting myself. Now what happens here is I have a single electron here and a single electron here. And this is where that master of the electron rule comes into play. So single electrons we know are bad, but what I can do is pick it up. Let me change colors, maybe that'll help. Pick it up and make a pair out of it. So now what I have is 3 bonds and 2 pairs, which is 5 total regions, which is why it's based on this trigonal bipyramidal one. So what happens is, it literally is the T shape. So we'll have our F. Let me actually make this bigger and bolder. Put my F right here, my F right here, my F right here, bromines in the middle, lone pair, lone pair. And I hope you can see where that comes from. Again, I want you to familiarize yourself with this and just don't sweat too much on details of this pod quiz, especially since we're at 20 minutes. Octahedral and square pyramid. Octahedral, what happens here is we have the S in the middle and 6 F's. Now, in order for this shape, or anything like this shape, to happen, S needs to be, again, on the third row or below, and it is. And SF6 would be octahedral, and that's what this shape would look like. Now, this is going to be much more difficult to see, and I'll probably do it in class. It's called octahedral, and octa you think would be 8, but it has 6 bonds. If you can see with the shapes that I'm making here, and there's one in the back, what happens is I've got 1, 2, 3, 1, 2, 3 sides you can see, and a 4th side in the back. So I have 4 sides on the top, and then I would have 4 on the bottom. 4 plus 4 would be 8. That's where the octahedral comes in. Square pyramid, hopefully you can see that on this one. The way it would look, let me shrink this back down a little bit more. XE, I'm going to go to black, would have a double bonded O, an F like this, an F like this, an F like this, and an F like this, and a lone pair. Well, actually, it's a single-ended O. Well, I should have actually drawn it out, but I didn't. But I'm not even sure if that's right, but I'm trying to cut down on this so we can go and be done. So it would be something like this, probably single bond. But anyway, we've got a lone pair here. So it looks just like the other one, but you have a lone pair that pushes a little bit harder. Square, planar, and T-shape, again, these again have 6 regions of negativity. Pair here, pair here. The T-shape would be, I'm just going to use X's and A's. T-shape would be, these are not real elements, but you can see what happens. This right here would be an A. And then I would have, actually, it would be better to draw it like this. Lone pair, lone pair, lone pair. Now, I will give you a huge hint. Central atom is least frequent. That is question number 1 on the podcast. This will take a ton of practice. Okay. Wedges come at you, dashed lines go away. Question number 2 on the podcast deals with that. 4 bonds is not 90 degrees. It's 109.5. That's tetrahedral. And you can't read that, but look at where it is before. That was number 3. And question number 4 would be, because this was so evil. Question number 4 is the only one you won't know, but I promise it'll be friendly. I'm sorry this went to 24 minutes, but hopefully you can look at it and watch it and go through it. We are spending a lot of time going over this again in class, so don't stress too much on it. Have a good one. Enjoy the Super Bowl. Go Bears. Well, I guess the Colts aren't in either.